Welcome along everyone. Today we're going to do episode 6, which is probably going to be the last one in my series on induction for pre-university physics or A-level physics as we know it here in the UK. So let's jump in. In order to start our understanding of transformers, we need to just refresh slightly what happens if we have a nice neat coil wrapped around an iron core and then we attach a AC supply to it like this. So we have an alternating current sloshing backwards and forwards, and as I'm sure you know, this is going to create a nice regular magnetic field with lines that look a bit like this. And of course, one instant in time these lines will be going up and then they'll shrink back down and the arrows will build back up, but in the opposite direction. So these poles are alternating backwards and forwards from north to south to north to south, and so on and so forth. Now you also know that in theory, if we put another coil near to that first coil, such as this secondary one here that I've wrapped on a what's meant to be a slightly amusing pencil, you will in fact induce an EMF in that second coil, assuming we have an AC here. Now this EMF that's induced is of course equal to the rate of change of flux linkage, but that rate of change of flux linkage is going to be pretty small for a couple of reasons, which we'll get to as we unpack the transformer. We might be able to get a slightly bigger, EMF induced in that pencil type thing, perhaps if we moved it kind of underneath or, maybe above. But either way, it's not going to be terribly effective. But the transformer is one of the best machines that us humans ever created. So let's jump in and talk about that now. So a transformer consists of a block of iron, as you may know. Now this iron doesn't have to be this sort of square shape, but it often is drawn that way. They come in all shapes. So we have two coils, and the coil on the left normally is known as the primary coil, or sometimes the input coil. So the primary coil is the one that's connected to an AC supply, like I've done there. And the secondary coil may or may not have the same number of turns, could have more or less, as in this case. And the secondary coil is wrapped on the same core, and we'll get a nice EMF induced. This will be a much bigger EMF. Well, it kind of depends on the ratio of turns, as we'll see, but either way, it'll be a bigger EMF. So how does this work? Well, the way it works is that if you imagine we just have a kind of a rectangular piece of, a bar, magnet shaped bar of iron for our core, you can see that the flux lines are going to sort of shoot off and make their lovely curves that they make. And in the transformer, you might expect that it will be something similar. In other words, the flux lines would come up and out. It's incredibly hard to draw these things, but like this. Well, in fact, of course, that's not what happens. The iron core is has two words that the syllabuses love to use to describe how they behave. And the first one is directs. So if you direct something, you kind of boss it around. So what the core does is it takes the lines that were travelling out and curves them around and literally provides I want to say resistance, but it's not the right word. that's for another day. It provides an easy path, let's put it that way, for the flux lines to travel around. So they literally just travel around the core. And of course they go around and underneath as well. Now some lines may well still come out of the core, but that's going to be very few now in comparison to what you had before. So that's the first thing. It literally directs those lines around. So the secondary coil over here finds itself sitting in and linking a whole pile of flux that has arrived or been produced in the primary coil. And the second thing that the syllabuses like to say is that the flux lines, or the core I should say, concentrates the flux lines. In other words, it brings them closer together. Now of course you know that if the flux lines are closer together, we get a stronger magnetic field. So together those two things help to make the transformer remarkably efficient creation by humans. Nothing that humans make is 100% efficient, of course, but the transformer does come quite close. So let's get a little bit deeper into the voltage now that's created in the secondary coil. So excuse me. In this topic, we know over and over and over and over again that the EMF induced is proportional to the rate of change of flux linkage. And you'll always see that, or often see it written with the N after the triangle, after the change, I suppose I should say. So you'll see it written like this. Now, what we're going to do is we're going to use that formula for the primary and the secondary coil. So in the primary, this time though, the same formula works, but this time, of course, what we're doing is we're providing the flux. No, we're not. We're providing an EMF that's changing, which is creating the flux. Either way, the same formula applies, and so we get voltage in the primary that's being supplied here is equal to the rate of change of flux linked in the primary. So in other words, we put NP, which is going to be the number of turns that we have there. In the secondary, we're going to get a very similar formula. That kind of will look like this. So in the secondary, we get voltage across the secondary is equal to the number of turns times the rate of change of flux. Notice I didn't say rate of change of flux linkage, although in many ways it amounts to the same thing. Having said that, in both formulas we have this term in common, and this means we can go ahead and bring these two formulas together. So a simple bit of algebra, we take Vp divided by Np, and then that's going to be equal to this change of flux term, and then on the other side we get Vs over Ns is equal to the jolly same rate of change of flux term. In other words, we can set these two expressions equal, and that leads us to the voltage in the primary divided by the number of turns in the primary is equal to the voltage in the secondary divided by the number of turns in the secondary. And there are various ways to write this formula. So you might see as Vp over Vs is Np over Ns. And the beauty of this formula is that because it's just ratios on each side and those two ratios are equal, we can just flip the whole thing over. It's a nice little algebra. I don't want to say trick because it's not a trick, but it's a really useful little thing to be able to do sometimes. So you literally just flip the whole thing over like that, and of course it still applies. So what we can see here is that the voltage on the input VPE and the voltage on the output V secondary depends on the ratio of the turns. So in our case here we have what's known as a step down transformer. So we might have something like the main supply, which you know of course, 230 or 240 volts AC, being stepped down to say something like 12 volts AC. So it's being reduced. Now there's lots of really good side effects here. This is used many times around your houses. For example, your phone charger, although it might make a different voltage to 12, the idea is the same. What's also, well, let's talk about step-up transformer briefly. So in a step-up transformer, a good example of that might be in a car. Say you want to turn 12 volts into 10,000 volts. Now it's not quite the same because we have a car battery which is DC, but it's the same principles. So 12 volts being turned into 10,000 volts. Now there's an issue here because 10,000 volts is fairly energetic and could give you quite a good shock. I mean, it's not going to kill you because, well, who knows? Let's not say it's not going to. Either way, it's going to hurt. So what might happen here is that the two circuits have become isolated through the core. So these two circuits are not touching. So as long as you keep this side separate from humans and only allow them to sort of touch this side, say with a on-off switch, they're not going to be able to touch the 10,000 and not risk an electricity shock. Anyway, that's kind of interesting, but perhaps a little bit by the by. So let's move on now and think about efficiency. Now, back in this slide, we said that we kind of waved our hand a little bit, if we're honest. You know, A-level physics does this all the time. Well, you know, it's around about this. We say that all the flux goes around that core. So the same flux is created as what ends up in the secondary. Now, because of that, we can make an assumption to derive this equation anyway, that a transformer is 100% efficient. Now, what this means is the energy on one side is equal to the energy on another side. Or to put it in terms of power, we could say the power on the primary is equal to the power on the secondary. Now, I worked in electronics for a few years and I got used to not writing primary and secondary, but writing power in and power out. But you can kind of see that they're the same thing really. What comes out on the secondary, what goes in on the primary. So just leaving that to one side for a moment, we're going to think now, we're going to pretend that our transformer is 100% efficient and work out a little equation. So this will mean that we have the voltage on the primary times the current in the primary has got to equal the voltage on the secondary times current in the secondary. Well, you know, so far so good. We can rearrange that one slightly to get then that voltage primary over voltage secondary is equal to current secondary over current primary. Notice that the P's are kind of on opposite sides of the fraction here, whereas earlier on in the last equations we did, the P's were kind of could go on the same side. Yeah, well, it shows it better here actually. Look, there's the P's are both on top. In our new formula, the P's are up, one's down, as it were. One's timesing, one's dividing. Okay, well, since we also know that the number of turns, so let's do, I just want to just jump ahead of slide. Since we know that the number of turns in the secondary over the number of turns in the primary is equal to the voltage on the secondary and the voltage on the primary, we can substitute in for this. So notice here that we have the opposite of that. Got S on the bottom, S on the top. So that means we're going to need to flip this one. But the upshot of all that is that we can say the number of turns on the primary over the number of turns on the secondary equals the current in secondary over the current in the primary. Notice again, if you've got what I was on about, that the P's are one's on the top, one's on the bottom. Alright, so this is an expression that helps us to do two things. This is our assumption about what is true if the transformer is 100% efficient, and from that we were able to work out a little formula that tells us about the current in the primary and the current in the secondary as compared to the ratio of the turns. But notice that nothing in the real world is actually 100% efficient, so we'll most likely have to say something like that the power in the primary is equal, no, the power in the secondary, let's do secondary, power in the secondary is perhaps only equal to 0.8 the power in the primary. That's a more realistic situation. But as I said, that's still 80% efficient. It's really high, so transformers are great. So let's think of a couple of reasons or a couple of ways that we can keep this this value of efficiency as high as it undoubtedly is. So I've dined out on this name eddy currents, being as it's my name as well. Anyway, leaving that to one side, let's think about what eddy currents actually are. So we've enlarged up a bit of the transformer here, and as you know, we have flux lines that will travel like this, and a fraction of a second later they'll be going back the other way. So the flux lines themselves, if you were to sort of think about their amplitude, you're doing a sinusoidal wave, maximum in one direction, maximum in the other, and going through zero. So the point of all this is that we have flux lines swooshing backwards and forwards inside a bit of iron, and iron of course has a whole bunch of delocalized electrons. In other words, it's a conductor. Now if you put a changing flux near electrons, those electrons will experience a force and they will start to move. So in other words, currents are induced in the core, and it turns out that these currents travel in circles, first one way and then unsurprisingly back the other way. So there are millions of these little eddy currents whizzing or sloshing round and round inside the coil. And of course the thing is, whenever you have whenever you have a current travelling through a conductor, you're going to get collisions, so to speak, which means you're going to get energy wasted as heat. In other words, this core is going to heat up, and the energy for heating up will of course come from the energy of the power supply. I mean, where else is it going to come from? So ultimately that's going to decrease the efficiency. And the way to limit this factor is using something known as a lamination or laminates. So let's talk about that. I'm always surprised when I tutor kids that none of them have actually ever seen a transformer. So anyway, here's a couple of diagrams. I mean, obviously you can just lift these off any search engine. So over on this bottom one you can see the two turns for the primary probably, and these two for the secondary. So in here will be a whole bunch of turns of copper, but what I'm really interested in is this sort of stripy affair here. These are layers of iron separated by layers of an insulator. We'll talk a bit more about how this works in a sec. In the second picture on this side we can see the same idea. We're looking at the core. This is obviously an old used transformer because you can see bits of solder on the connecting leads there. So it's been taken out of a circuit. Underneath this tape will be a bunch of many turns of copper that are kind of going like this through the core. But anyway, the point is you can see the laminations, the strips in the core. So how this works, this is a nice bit of physics, this, is that in the core you have layers of insulator. Now I've only drawn a couple. It might have been better if I'd done a few more, but anyway, there they are. Layers of insulator and layers of iron. So it's like a sandwich: iron, insulator, and so on. Now what happens is that the eddy currents can't travel through the insulator. They can only travel through the iron. So instead of going perhaps like this, let's draw a big one, going from kind of the top to bottom of our core, they're now limited because they have to fit in this gap because they can't go through the insulators. So they would have been this size, and now they've been reduced by the insulators. Now if you imagine that going on many times with all the different layers, excuse me, the effect is obviously to reduce the current flowing in that core. If you reduce the current flowing in the core, you're going to reduce the heat loss through the current flowing and hitting into the iron particles in the lattice there. So in other words, you're going to reduce the energy wasted. It's not going to be as inefficient as it was. But the trouble with this, of course, is that within a given mass of transformer, you've now reduced the mass of this actual iron because you put layers of insulator in there. Sorry about the coughing. So the point being that you've actually reduced the size of your iron. So this is a toss-up here. You have to balance between reducing the currents but also reducing the amount of iron. You want the biggest lump of iron you can get because that will be more efficient at sending over the flux lines. But if you put bits of insulator in, you're obviously reducing the size of your iron. So probably somewhere on DuckDuckGo or your search engine of choice, there are equations that you can use to balance this, not that you need to know about them. But that's the first thing that we can do to make the make the coil or the core as efficient as possible. The second thing is actually the material that you make the iron out of, and it's called soft iron. This has nothing to do with how hard it is, although the opposite of soft iron is actually known as hard iron. It's got nothing to do with whether you can squash it or not, which is normally what you think of soft. So if you remember back in the day when you were little perhaps and you got the chance to play with bar magnets at school, although again so many of my students don't get to do this sort of stuff, you could hang a bunch of paper clips onto a magnet. There they go. Great exciting physics practicals. And then if you take the magnet away, what you expect is that all the paper clips will separate. But after you've done this a few times and you take the magnet away, those paper clips manage to retain some of their magnetism. And whilst you may not be able to get 3 to stick in a line, you'll certainly be able to get 2 to stick to each other. So what's happening is it's almost as if there's a memory. In fact, that's exactly what it is. It's like there's a memory inside the steel or whatever it is the paper clips are made of. Now that's great if you want your paper clips to stay magnetic, but it's not great in a transformer, because what you want is you want the core material to lose its magnetism as quickly as possible. And the best material for that is soft iron. So if you look at the flux that's going around the coil, around the core, there we go. As we said, it's a sine wave directly related to the current that's producing it. If you look at that line, you could scrub this out here, and we could say have it as the amount of magnetism that's stored in the actual coil itself, in the core itself, and you want that to follow the same shape, to go through the zeros quickly and efficiently and not have a memory, because you could get a situation where the core has become slightly magnetic, let's say in this direction, and the flux lines are traveling the other direction. So now you've got two opposing magnetic fields due to the memory in the hard iron, because it's the hard iron that has the memory. So we need to get rid of that and use soft iron so that there is no magnetic or very little magnetic memory in the iron itself. So those are the two ways that you can make a coil or a core or a transformer even more efficient. So let's move on, and it's always good to do an exam question, isn't it? So it's a typical AQA one, as it is in this case. This won't take a minute because it's not that difficult really. It's just, just get a few facts in your head basically. So explain the purpose of the core. Well, we said there's those. So figure 1 shows a step-down transformer. Explain the purpose of the core. Well, as you might expect, it's to direct and concentrate the flux lines, just like we said earlier on. All right, so the next one then, it says, says describe two features of the coil that will improve the efficiency of the coil. And I've just scrubbed, I just missed a page. So describe and explain two features of the coil to improve its efficiency. So the first one, you could just say include laminates to reduce the eddy currents. You might want to say something, actually looking at this again, that the laminates are layers of non-conductor to reduce eddy currents. A little bit more detail there. And the second thing would be to say use a soft iron core so the core loses its magnetism quickly. So there are two features that will make it more efficient. Next up then, explain why a transformer only works continuously, key word, when supplied with an alternating current. This is only one mark, this question, and which kind of hints at it being they want a simple answer. And the answer for this, of course, is that the EMF is equal to minus delta N phi over delta T, and you know that equation again. If there is no rate of change here, in other words, if the EMF is constant, if the flux is constant and not changing, you're going to get zero EMF. And you want the transformer to be constantly changing, in other words, to be constantly producing an EMF. Now, I suppose you could say that if we get an output like this, the voltage is, for a fraction of a second, zero. But the fact is as when it goes through that zero, it's in the process of constantly changing, because it's going from being positive to negative. So it is in fact constantly supplying an EMF. It's just it's a changing one. So don't get worked over or worked up about this word. What you need to do in order to answer this question is to simply point out that alternating current is constantly changing as well. You know, reflect back the question terminology here is constantly changing, or continuously, you know, constantly changing. So AC is constantly changing and EMF is proportional to the rate of change of flux linkage. All right, and that's your answer for that one. Okay, so moving along. So now we have a little calculation to do. So it says the primary coil is connected to 230 volts. Notice the RMS. This is the first time this has come up today. If you're going to do anything about power with transformers, and that's where we're going with this one, because look, it says power, you have to use RMS figures, and I explained that in my induction section 5, so maybe check that rather short live stream out as well, and that will help you to understand that. So doing this question, then we have 230 volts on the primary, so 230 volts over here. The current in the primary is 0.3 amps. Always good to put labels onto the diagrams. The secondary has 300 turns and provides an output of 20 volts and a power of 65 watts. So we've got a whole bunch of figures here. It says calculate the number of turns in the primary there. Okay, so that's our first question. And in order to do that, we look at the figures and then we just use the formula. So really it's dead simple. We just know that we have NS over NP equals VS over VP, and we've got the voltages, so we've got one of the turns, so we just chuck in the numbers. Now we need to find the turns in the primary. Now I made a small teacher error here, because look, I've put NS over NS when it should be NS over NP. So we have to find NP, which is the one on the bottom. Now for easy algebra, I'm going to flip. So we're going to get NP over NS equals BP over VS. Take that NS, stick it up there. So now we have that NP equals NS VP over VS. And if you put in the numbers into that, you get 3,450 turns, which is a lot of turns, isn't it? A lot of turns, but nevertheless, that's what it is. Now I'm just going to check we got that right. Yep, 3,400. Last part then, calculate the efficiency of the transformer. Now we know that coming out of here is 65 watts, I believe. I might need to look at some numbers here. And the efficiency is going to be given by the power out, or the power in the secondary, over the power in, power on the input. So we know that the power out is 65 watts, because we're told that. So in order to get the power on the input, we just need the voltage times the current, and obviously don't forget both of those have got to be RMS values. So that gives us 65 watts divided by the values that we picked up from the previous question, which is 230 and 0.3. You can see them there, 230 and 0.3. So 230, that's an RMS value, times 0.3, that's an RMS value too, which gives us 65 over 69, which is about 94%. And you know what, that sounds terribly high. Maybe it is a little bit, but it's not unrealistic for a transformer, which is just amazing. If we can make cars that were that efficient, well, how good would that be? I don't know how good it would be, but it would be good. Right, well, hopefully that was useful. I don't think transformers are that difficult, really, if you just learn, as I said, a few key facts. So anyway, do let me know if that was useful, and I'll see you next time.